Welcome to our series on RAG, Retrieval Augmented Generation. We're experimenting with new ways to teach AI. First one is using popular storylines to make complex concepts stick. We really want to know, is this working for you? Whether it's too simple, too dense, or just right, your feedback helps us improve. Leave a comment with your thoughts, what works and what doesn't, or perhaps suggestions for future topics. If you find this helpful, don't forget to like and subscribe.
Welcome to our deep dive into the architecture of modern information retrieval. Today, we are exploring the critical technology underpinning the latest large language models, the intelligence pipeline. We call this entire systematic process target acquisition. In a world increasingly drowning in information, finding the one precise verifiable fact you need is no longer a simple database search. It is a complex, strategic military operation requiring multiple phases and specialized tools. This presentation offers a comprehensive strategic overview of how we execute these high-precision retrieval and ranking operations. Think of this as the playbook for turning unstructured, chaotic data into verifiable, actionable intelligence that LLMs can trust. We will unpack the specific tools and technical techniques used to ensure that when a large language model asks a question, it receives not just an answer, but the single most accurate and contextually relevant piece of information available. This pipeline is the foundational architecture of trustworthy, non-hallucinating AI systems, and mastering its components is essential for anyone building next-generation knowledge applications that demand accuracy. The premise of our entire mission is simple but profound. The battlefield is information. Look around the modern intelligence landscape, and all you see is a vast, challenging sea of unstructured data, ranging from internal reports to external documents, transcripts, and operational logs. Our users, or decision-makers, fire off an incoming query, which we classify internally as a high-priority request for information, or RFI. This RFI demands one thing, and one thing only: a single, correct, verifiable answer drawn from potentially millions of source documents, all delivered almost instantaneously. When operating under these stringent conditions, speed is certainly critical for ensuring a good user experience and system responsiveness, but precision is absolutely paramount and non-negotiable. Consider the devastating risks involved. If we feed the ultimate decision maker, the large language model, flawed, outdated, or irrelevant intelligence, the immediate result is mission failure, or what is more commonly known in the AI world as a hallucination. Hallucination occurs when the model fabricates a response or weaves facts together incorrectly because the context provided was either misleading or fundamentally insufficient. Therefore, our overriding objective is crystal clear. We must engineer a reliable system to find the precise chunk of data, the specific high-value target that directly answers the RFI, and deliver it reliably, accurately, and quickly to the consumer. This high-precision requirement drives every architectural decision we make in this sophisticated intelligence pipeline. Our first phase of target acquisition involves deploying the initial search teams, a dual force designed to maximize coverage and retrieval speed across the entire document corpus. Our first agent is the Infiltrator, which executes a vector search. This operative is a master of stealth and deep conceptual understanding. The Infiltrator does not look for exact keyword matches. Instead, it converts both the query and the documents into numerical vectors and searches for conceptual or semantic meaning. It identifies documents that feel semantically similar to the mission objective, leveraging nuance and complex semantic relationships. The Infiltrator helps us find documents that discuss a topic without necessarily using the exact vocabulary from the query. Contrast this approach with our second operative, the Sentinel, which uses the traditional BM25 algorithm. This is our direct action specialist. The Sentinel conducts a loud, fast sweep strictly for exact keyword matches. They are ruthlessly efficient at finding explicit terms mentioned in the RFI, focusing on term frequency and document length. The Sentinel guarantees that no obvious, literal lead is ever missed. By deploying both teams simultaneously, we ensure we capture targets whether they are hiding in plain sight with keywords or camouflaged conceptually with complex language. As we just discussed, neither the Infiltrator's semantic intel nor the Sentinel's keyword intel is perfect or complete on its own. The Infiltrator, focused on deep conceptual meaning, might easily overlook a trivial but highly important proper noun or a specific acronym used only once. Conversely, the keyword-based Sentinel lacks the sophisticated contextual understanding to truly rank documents by relevance, often erroneously promoting low-value documents simply because they contain a high density of matching common words. To decisively overcome these individual weaknesses and capitalize on both search paradigms, we must strategically combine their findings into one unified, superior operational plan. This is where Reciprocal Rank Fusion, or RRF, steps in, effectively acting as the field commander for the data. RRF is a powerful algorithm that takes the independently ranked lists from both the vector search and the BM25 Sentinel and mathematically fuses them together. Instead of simply averaging their relevance scores, which could dilute the results, RRF prioritizes documents that rank exceptionally highly in either list, assigning them a strongly weighted score. The outcome is a fused target dossier, a highly optimized, single-ranked list that leverages the unique strengths of both semantic and keyword retrieval, delivering a significantly more robust and accurate set of initial candidates for the next critical phase of verification. Despite the speed and comprehensive coverage of our initial hybrid sweep, there is a critical flaw in high-speed surveillance. Our initial retrieval models can be fundamentally blind to critical structural nuances. The models we use in Phase 1, the BI encoders for vector search, analyze the query and the documents separately. They compress the meaning of the query into one vector and the meaning of the document into a different vector. This parallel compression is exceptionally fast, but it critically loses the ability to recognize grammatical relationships and the structure of the sentence. Consider the two phrases illustrated here: the snake bit the dog versus the dog bit the snake. In a high-dimensional vector space, the essential component words are identical, and the vectors might show a similarity greater than 95%. This close similarity score represents an unacceptable intelligence failure. The model cannot reliably distinguish aggressor from victim based on the grammatical context, meaning highly relevant but distinct facts can be easily confused. We urgently need a specialist who can read the documents interactively and contextually to truly understand the nuanced relationship between the words in the query and the words in the context. Our initial hybrid search has served its primary purpose. It efficiently reduced a massive volume of 5,000 raw intelligence reports down to a manageable dossier of the top 50 potential targets. Think of this initial process like an automated resume screening system that flags 50 candidates out of thousands for manual review. While fast, the tool is inherently blunt. It might mistakenly flag a highly qualified Python ecologist as a suitable candidate for a demanding Python developer job simply because of the shared keyword Python and the semantic proximity of coding terms. Now, precision becomes absolutely paramount, and we must call in the specialist, the cross-encoder analyst, often referred to as the reranker. This analyst does not waste time rescanning all 5,000 documents, which would defeat the purpose of speed. Instead, they carefully read and deeply analyzed just the 50 candidates flagged by the automated screen. They meticulously analyze each one for nuance, context, and true relevance. They then reorder this small list, moving targets from must investigate all the way down to irrelevant based on deep contextual interaction. This two-phase strategy is fundamental to balancing performance requirements. The retriever, composed of the Infiltrator and the Sentinel, gives us the required system speed, but the reranker gives us the surgical precision needed for guaranteed mission success. Let us now take a look inside the analyst's toolkit and meticulously contrast the mechanism of the high-speed BI encoder with the high-precision cross-encoder reranker. On the left, we observe the independent analysis strategy utilized during our retrieval phase. The query and the document are processed by two completely separate transformer networks, resulting in two distinct numerical embeddings. Vector A and vector B similarity is then calculated by cosine similarity, which simply measures the spatial distance between the two vectors, yielding a score, perhaps 0.92. Critically, the processing paths remain strictly parallel, with absolutely no crossover or interaction between the query tokens and the document tokens during the encoding process. Now, shift your focus to the right side, which depicts the simultaneous cross-examination performed by the cross-encoder. Here, the process is fundamentally different. The query and the document are strategically concatenated or joined together, separated by a special SEP token that signals the context break. This single, combined input sequence is then fed into a massive, unified BERT model. The true innovation lies within BERT's powerful self-attention mechanism. Because all tokens, both from the query and the document, are processed within the same context layer, the model can examine the interaction, dependencies, and grammatical relationship between query words and document words directly and simultaneously. It can therefore accurately understand that snake, biting dog, is a fundamentally different action and relationship than the reverse scenario. This interactive analysis allows the cross-encoder to produce a highly granular relevance score between 0 and 1, ensuring its precision is far superior to that of the initial parallel retrieval phase. While the cross-encoder offers unparalleled precision and accuracy in ranking, it unfortunately comes at a significant computational cost, leading us to discuss the high cost of precision. The bottleneck inherent in this technology is clear. Cross-encoders are exceptionally computationally expensive and consequently very slow compared to the simple by-encoder retrieval models. They must perform that complex, token-by-token simultaneous cross-examination across all words we just discussed, which requires enormous processing overhead. Asking a cross-encoder to analyze 1 million documents for a single query would be analogous to assigning a senior intelligence analyst the impossible task of personally reading and verifying every single raw intelligence report from the entire digital grid. Such a task would take hours, or potentially even days, which is simply unacceptable in any real-time application setting. To definitively solve this critical scalability challenge and maintain speed, we rigorously follow the two-stage doctrine. Phase 1 is retrieval, which must be fast and broad. Here, we leverage the highly efficient by-encoders and keyword search mechanisms to perform the initial funneling, reducing 1 million documents down to the top 50 most likely candidates in seconds. Phase 2 is reranking, which is inherently slow and deep. We then strategically deploy the expensive, high-precision cross-encoder only on the small, pre-filtered list of 50 candidates. This approach allows us to surgically identify the absolute top 5 documents with guaranteed, high-caliber precision, ensuring we successfully maintain speed while achieving peak mission accuracy. Once we have identified the final top 5 documents through our rigorous reranking process, our mission is still not entirely over, because we must next take steps toward defeating cognitive camouflage. Large language models have a known and well-documented cognitive bias when consuming long inputs. When presented with a long list of documents, which constitutes the crucial context for generating an answer, they pay most of their attention to the information located at the very beginning and the very end of the list. Conversely, critical intelligence can be easily ignored and missed entirely if it is buried somewhere deep in the middle of the context window. This phenomenon is commonly referred to as the classic lost-in-the-middle problem, and it directly compromises the final output reliability. As the U-shaped performance curve clearly shows, the accuracy of the final answer dips significantly when the relevant information is placed in the center of the provided context. This unfortunate consequence acts as a form of tactical camouflage. The high-value target is hiding in plain sight, deliberately using the surrounding crowd of other semi-relevant documents to evade detection and accurate processing by the LLM. We must actively counter this inherent bias. The countermeasure to the lost-in-the-middle problem is straightforward yet devastatingly effective. We must actively use our intelligence tools for the strategic goal of forcing the target into the spotlight. The reranker is essential here because it doesn't just categorize documents as generally good or bad. It assigns each one a precise numerical relevance score, such as 0.98, 0.45, or 0.12, quantifying its fitness. The action is to use these highly accurate scores to strategically order the final dossier before we hand it off to the large language model for synthesis. By sorting the documents strictly by their relevance score, we guarantee that the document containing the most critical, verified information, the one with the 0.98 score, is placed at the absolute top of the input context. This placement ensures the high-value target falls directly within the LLM's peak attention zone, where performance is optimized. We effectively overcome the LLM's known cognitive bias, guaranteeing that the most critical intelligence is seen, processed, and used in generating the final response. The target is successfully flushed from its protective cover and secured for mission execution. Even after successfully reranking and strategic reordering the top 5 documents, we face one last efficiency challenge: the final inefficiency. We have successfully identified the top 5 most relevant documents, but those source documents might be extensive reports. A single document could easily be a 10-page operational report where the actual, precise answer is just one single sentence buried in the middle. Sending the entire, full report into the LLM context window is extremely inefficient and costly. First, it increases the operational cost by wasting valuable context tokens which are expensive to process. Second, it significantly increases latency, slowing down the overall response time for the user. Most importantly, it introduces noise. Irrelevant text can distract and confuse the LLM, potentially causing it to incorporate secondary details or struggle to pinpoint the core fact required. The solution is contextual compression. After the documents are re-ranked and reordered, a lightweight extraction model scans the top documents. This model performs the final edit, executing a trimming operation that extracts only the relevant sentences that contain the direct answer to the specific query. As shown in the example, we transform a large original chunk containing filler text into a concise compressed payload. This final trim operation ensures the LLM receives the absolute maximum factual signal with minimum distracting noise, optimizing the final mission execution. Let us now review the complete target acquisition process one final time, encompassing our comprehensive mission profile, from raw data to actionable intelligence. This rigorous flowchart visualizes the entire 6-stage pipeline necessary for achieving high-precision information retrieval at immense scale. It begins with Stage 1, Ingestion and Indexing, where raw intelligence documents are meticulously processed, parsed, and indexed into a centralized, searchable grid, including the crucial vector database. Stage 2 is simply the query, the critical moment the user issues that incoming high-priority request for information, which triggers the entire cascade. Stage 3 is hybrid retrieval, where the Infiltrator, our vector search component, and the Sentinel, our BM25 keyword search component, perform a broad-spectrum sweep simultaneously. Their individual findings are then efficiently fused using the powerful Reciprocal Rank Fusion algorithm, yielding our highly refined initial list of 50 candidates. Stage 4 is reranking, where the specialist analyst, the powerful cross-encoder, performs a deep cross-contextual analysis on only those 50 candidates, verifying relevance and context. Crucially, it then reorders them based on precise relevance scores to secure a guaranteed top 5 list. Following this essential verification, we move to Stage 5, compression. A lightweight extraction model scans the top 5 documents and extracts only the key, most relevant sentences that contain verifiable facts, eliminating all surrounding noise and saving precious processing costs. Finally, Stage 6 delivers the final payload. This is the perfect, augmented prompt. The user's original question is strategically paired with the exact, verified, and compressed facts, delivered to the LLM in the optimal order for immediate attention, ensuring successful and completely hallucination-free mission execution. This rigorous, multi-stage pipeline is the modern mechanism that transforms a chaotic, vast data environment into a reliable, verifiable, and actionable source of intelligence for any advanced AI application seeking trustworthiness.